I'm very happy to be the one introducing the next two speakers for the first session here. I'll give, since everybody introduced themselves already, I'll give most of the little time that I have to give you a background on how the projects that you're going to be hearing about sort of got started and got together. So a couple of years ago, I read this very interesting paper that Kevin's group published about having done a long-term deployment and evaluation of model predictive control in a residential building, fully electric, near the Purdue campus. And Ozan and I, Ozan, my student, and I, when we read that, we were like, oh, this very cool opportunity to test things in the wild. And we had been working on a similar HVAC controller that was based on reinforcement learning. And we said, hey, why don't we reach out to Kevin? Ozan had been in this IBO event, I think in 2024 in the summer, and had met Kevin directly. I also had met Kevin before. And so we reached out and decided that it would be nice to join forces and figure out if we can do a comparative analysis. And so Ozan met up with Elias. Elias and Ozan worked really hard to sort of try to do a apples to apples comparison of what RL could do in the same building and what MPC could do in the same building. The rest is history. We now have a paper that is under submission, under review, I should say, on this topic. And you'll hear sort of like the background of both perspectives and what we could learn from that project. So I think it's a very exciting opportunity, especially because most of the work that has been done, and for good reasons, in evaluating controllers has been done in simulation. And so getting these things to work in practice is kind of very important, but also very hard to achieve. So you'll hear about the pros and cons of having done this, and hopefully that'll incite discussion for the group going forward. So without further ado, I'd like to have I don't know if it's Elias or Ozan that's starting, but let's hear the presentations.
That sounds great. I think we can start with Elias. And Elias, would you like, if folks in the room have questions, would you like them to hold the questions until the end of your 15, 20 minutes here, or just ask as you present?
They can ask as I present. I don't really mind. Thank you.
Okay, sounds good.
Is the slide deck coming through?
Yeah, we see your PowerPoint window.
Okay.
And your slides. That's great.
Okay. All right. So welcome everyone to the first presentation. Thank you for having me on board this morning. So the topic, as Mario discussed, we're going to talk about the comparative field deployment of model predictive control, MPC and reinforcement learning, RL, for residential HVAC. Now, the study hasn't been hasn't been published yet. There is an archive version up, and these were the participating authors in this effort. And my name is Elias Pergantis again, and I will be presenting the model predictive control part. So this is a study that was performed a few years back. Take you over through the methodology, all the parts that went into the controller, and then the performance results. So the study, let's first talk about the aim. Okay, there has been specific deployments of RL and at residential buildings and commercial buildings, as well as MPC at both residential and commercial buildings. But it's very rare to have head-to-head comparisons, especially at the same building, and that can give us a lot of information in terms of the relative controller performance, data limitations, how long does it take to implement a controller? So all those are very relevant questions when we talk about scalability of these technologies. So in terms of the original MPC study, these were the dates of the experiment. It was carried out between January 30th to March 30th of 2023. So 3 years ago. The total experiment duration was 59 days, of which 33 days were of active testing. So the remaining days were done both for baseline purposes as well as data loss. I would say probably 10 or 15 days we lost to do that. So we did discover a lot of issues in terms of when you field. This was our first field deployment, and we were learning a lot in real time. So connectivity and sensor maintenance, as well as API-related communication issues, especially the thermostat that did prove to be a bottleneck because we didn't have, we had a third-party HVAC manufacturer thermostat versus having, let's say, ecobee or a Nest or something that allows you more active control of the system. But because we had a variable speed heat pump, we had to stick with a manufacturer's thermostat. So the weather, the house was in West Lafayette, Indiana, as mentioned. So we did have some very cold days down to minus 15 Celsius or 5 Fahrenheit for the Imperial folks. In terms of the energy savings, we did some, I'll go back to how we calculated this number, but our 95% confidence interval was between 13 to 24% with an expected value of 19%. And critically, we were able to reduce backup heat by 40%. And yeah, this is the publication record for this. So going into the test bed, so the house, the location, West Lafayette, Indiana, the climate code is, with ISCC, it's 5A. It's a 208 meters squared with 3 occupants, full electrified home. The equipment, centrally ducted variables speed heat air source heat pump. So that means it's air to air with the ducting system delivering heat or cooling throughout the house. The installation is in the basement of the house. The system is a variable speed mid-tier Trane system, so it's not a cold climate heat pump, and it has a heating seasonal COP of 2.5, and it has 3 strip heat elements, each one of different electric capacities that you can energize. So each stage delivers either 9.6 or 14.4 or 19.2 kilowatts. And this strip heat is used both for defrost purposes as well as meeting the building demand. So when you go into defrost, strip heat is energized to meet the building load while the system is running in cooling. This is the house. I'm sure some folks will also visit it over the weekend. But in terms of the IoT, Internet of Things, the infrastructure, I would say these were the 3 main systems that we used for the study. For training purposes, I would say that you only really need the electrical data and the thermostat measurements. So we had current transformers in the breakers to monitor all the different subcircuits by iota watt. We had this Trane thermostat that we can read the humidity and the temperature at the central location. This is the living room of the house. This is not a zoned building, I should say. And then we also had some thermocouples and airflow sensors that were used to understand more broadly the thermal response of the building. And those are intact. Now, once you do have the sensors, we developed, we had Raspberry Pis for some of these, but for others, just through direct API communication, we were pushing the information to InfluxDB on AWS server. So this was used for data storage. And then in terms of actively controlling the system, we could have run the optimization remotely on the server as well, but for monitoring and other privacy and control purposes, we were running this on a local computer, which is solving the optimization problem and sending a set point for this specific problem. We've done other studies with water heaters, with EVs, but for the specific study, it would decide the set point and push that to the thermostat. Okay, so do we have any questions so far in terms of the house or the infrastructure?
I've got one question, I guess. How old was the existing heat pump?
So I believe it was installed in 2020. So 3 years, I would say. We didn't do any additional. We do monitor the charge of the system, but we do let it be as if it's operating in a real house. So we try to have as little intervention and use external third-party dealers. Does that answer your question?
Yep, just making sure it wasn't like 20 years old.
Yep.
A lot of heat pumps have them well. Yeah.
I just have one question about so you said the MPC is running locally on Pi, and then it pushes basically, is it pushing the set point value directly to the thermostat, or are you going to I'm just curious. So you also have the influx dB. So what is that? Is that just basically for data storage? How does the set point signal get to the thermostat?
Exactly. That's we could have. So we have the server, and we could have been doing all the calculations and the API pushes to the thermostat remotely. But as you mentioned, we solve the problem. We don't really solve it on the Raspberry Pi, although we could. It's the formulation is convex, and we can solve it in a Raspberry Pi, but we were using more traditional desktop computer with Windows, running MATLAB and solving the problem. And then we do push it directly to the thermostat. So we could have just sent a value to the server, and then the server send it to the thermostat. But this is through the internet, the API communication, so it can be done either within the house or from the server, and we chose to do it through the house. Does it answer your question?
I think so. So it's basically the whole problem is being solved locally, essentially.
Exactly.
Like a desktop computer that you guys have.
Yeah, it's a computer based on. It could be implemented.
Yeah, I was just curious.
Device that we did. Yeah. And there could be a feedback loop going from the InfluxDB back to the local desktop, because I think, Elias, correct me if I'm wrong, but I think that you pull power and temperature data from Influx back to the local desktop.
Yes, that's I guess a good arrow that's missing from this. That closes the loop, so there is information shared from the optimization problem from Influx. Of course, we need to pull the measurements from the house, and also the weather. The weather, we don't really store it on the server. We just have an external weather service that we query every time we are solving the problem, which is Oikolab for folks that are interested.
Okay, I think that's all the questions from the room for. Thank you.
Okay, thanks. Now we'll go back to this. I don't want people's eyes glazing over, but effectively, this is the problem that we are solving, the optimization problem. We have the object. I'm gonna talk about most of the different parts that make the problem in later slides, but at a high level, we have an objective function that balances comfort, reducing the total energy consumption, electricity consumption, as well as reducing the peak that the system uses. That's really in place to penalize strip heat usage. Then we have dynamic model for the house that was trained on real data, and it's a 2R 1C model. We're going to talk about a decision, I believe, in the next slide. And then in terms of we get the initial conditions, which is what's the temperature at the house at the instance where the optimization problem is solved. Then for the equipment model, we have this mapping between the capacity to electrical power. So if the real building demand is greater than what the heat pump can deliver, the rest of it is being delivered by strip heat at a COP of 1. So that's how we calculate the electrical power. And we also have constraints in terms of how much heat can the system deliver at a given instance, as well as some hard comfort constraints. We do have also soft constraint, but hard comfort constraint ensures that we never deviate too drastically from the preference that the homeowners have. The formulation is convex and is solved using CVX in MATLAB. The forecast horizon is 24 hours at a time step of 1 hour, and the set point is pushed to the manufacturer thermostat. Do we have any questions about the formulation?
Yeah, I have a question about that. So you guys understand it, right? So you guys solve the problem using assuming like a fixed heating COP. Is that right?
Actually, the COP, I should have it as a parenthesis because it's a function of time as other system variables. It's an open loop. It's open loop model. That's not correct to say, but it's only function of ambient temperature. It's not a function of the indoor conditions, because if it was a function of the indoor conditions, then that would be one of the, that's also what the decision variable for the system is. So once we predict the weather going forward, we can also predict what the COP of the system is going to be over that prediction horizon.
Yeah.
Does that make sense?
Yeah.
I had a quick question. In your equipment model, is the max term missing a comma 0 or something? Or is it truly the largest of a time series?
For the heat pump.
Yeah, so it says equipment model P equals Q dot C over COP plus and so forth. And then there's a max term, right?
Yes.
Is
yes,
this a max?
That's correct. Yes. This equation was ported over early this morning, so mistakes.
So it should be comma 0, right?
Yes, that's correct.
Okay,
It
so it's not
0.
the maximum of a time series. Okay, got it.
Yeah. It has to be positive, at least in heating. So it could be based on the mode, but yes, it's comma 0. And I should also mention that the heat pump maximum power is also a function of ambient temperature.
Yeah. Thank you.
All right. Again, we're going to go back to this. So if you have any questions, I think that the next slides are going to answer them. Let's talk first about the gray box model identification. So for simplicity and scalability, we use the 2R 1C model, which we solve this problem using least squares because we don't have any unobserved parameters. Unlike, let's say, a 3R 2C or higher order model where we would have temperature of the mass, which might not be observed. Once a model is found, we use a support vector machine to fit and achieve improved model closure. So in the previous slide, this is effectively this term. We have a term for people's activities and model accuracy and other error terms all lumped into an exogenous term, and that's support vector machine as a function only of outdoor conditions. In reality, it should really be both of indoor and outdoor conditions, but to maintain linearity and convexity, we have it only as function of outdoor conditions. And that does improve model accuracy in capturing some effects such as solar gains and other things that we don't explicitly model as part of the main equation. So we use 30 days for training, of which we use an additional 14 days unobserved for validation purposes. The root mean square error for the one-step prediction was 0.4 Celsius, and for the power, 2.3 kilowatts. And this is how the model performed. In general, we found that we were able to train the core RC parameters with significantly fewer days than this, but really we needed a longer period of time to train the machine learning portion of the model. And these temperature swings we are seeing here is we didn't do any active excitation for the building. Instead, we were just having a schedule. So during the night, and we would lower the temperature, and during the day, we would increase the temperature. And that does help uncover some of the dynamics that the space has. It's not ideal, but it doesn't cause any discomfort to the homeowners as opposed to randomly adjusting the temperature. Especially because I should mention the occupancy for this is not what the reason we didn't use occupancy as part of the optimization is the house is more or less occupied at all times. There's not like a typical family home where maybe the people leave during the day and come back from work. Instead, we have occupancy most of the day. Okay, do we have any questions in terms of the model training?
Sorry, so you're saying for the training portion, that's why you're seeing the swing, like the larger swings?
Yes.
Okay.
Okay, so
in the interest of time, I'd like to say roughly half the hour for Ozan, which gives you about 10 minutes. So maybe we'll try to hold questions a bit so you can get through. Thank you.
Yep. So I guess let's hold the questions at the end of the presentation for the time being. In terms of the optimization, we don't have really active control of strip heat. In addition, to maintain convexity and not really look at the cycling effects of the indoor controller, the time step is 1 hour. In order to do that, we use the expected system capacity to create this mapping from thermal capacity to electrical power. And basically, this is how it looks. We look at the heat pump portion, and then after the heat pump portion, we assume that the system is operating at strip heat power, which is at the COP of 1. In terms of the COP of the system, this is purely a function of ambient temperature, and we can see how it looks. The variation from the points is because of different indoor conditions. So we can see indoor temperature definitely does have an effect, maybe 10 or 20% COP difference, but the main trend is driven by the ambient temperature. Now, in terms of the objective function, we briefly covered this before, but we had 3 terms. First, the power penalty. This is not a real penalty that the utility has in place. It's based on typical demand charges, and the units are $ per kilowatts, and it's aimed towards softening the power profile of the system. Then we have the energy. This is aimed at reducing the total electrical energy consumption. It's dollars per kilowatt hour, and it's defined based on local electricity prices, and it's a flat rate. There was no time of use present. I believe it was during the time of testing $0.14 per kilowatt hours. And then lastly, for the discomfort, The absolute term is there in order to avoid deviation, both upwards and downwards, from what the homeowners really want. And the units are in dollars per degree per hour. And the optimization basically needs to balance these three terms, and it's not trivial. How do you, especially the discomfort price didn't have necessarily physical units that we could easily tune. To do this, we found that we started with some price, and then we found that generally, as the weather fluctuates significantly at the location, we would find that the optimization would not really honor the comfort aspects of the bargain at different weather conditions. So, because if this is tuned at, let's say, 0 degrees Celsius, and then we go to -10 the next day, then you can imagine we are trying to only solve for the energy portion. So our solution to that, we once every 12 hours, we would simulate the system effectively with different comfort penalties, a range of comfort penalties. And we can do this quickly because the problem is convex and solves very fast. And it allows us to identify thermal comfort prices that ensures the indoor PPD is less than 10%. So that's very important. That's just generally what ASRI uses for comfort. We used some sample clothing and have some questions for the homeowners on that. And then this is how this looks effectively on a cold day. We effectively swipe the thermal comfort price, and we can see the lower the thermal comfort price, the more the savings, but also the more the discomfort. And we find the comfort price that ensures the PPD over the forecast horizon is less than 10%. And likewise, we do this on a mild day, and we can see that the price is much lower, right? So we have more freedom to optimize. So that ensures the controller is doing its best regardless of the weather. How did the controller do? What were the results? Now, I would say the controller learned two different things. One is to prioritize heating at milder conditions, and secondly, to recover from setbacks very slowly. Both of these, you could do with a heuristic, and there is also smart recovery algorithms in there. But a lot of the savings actually of the algorithm were just by slowly ramping up the temperature over a couple of hours with some homeowner discomfort, but being able to avoid using electrical energy, at least for indoor conditioning purposes, but occasionally for power purposes. So, the figure on the top, each of these instances is actually a defrost cycle. And, when we integrate this electrical power signal, we find some savings. I believe for this specific day, the savings were 18%. And since the temperature is colder on average for the indoor space, we normalized the indoor, and for the MPC case, we normalized indoor-outdoor temperature difference, which means that the MPC is on a much colder day than the non-MPC constant homeowner hold. And I should have mentioned earlier in the study, the baseline controller is just the homeowners doing what they want with the thermostat, occasionally having schedules, disabling the schedules based on their preferences. Now, this is another day, and this is a day we schedule, and we can see critically that when the system is recovering, even at relatively mild weather conditions, it would use a lot of strip heat by just increasing the set point suddenly, whereas the controller would have a similar recovery and also on a much colder day, but would do this just gradually increasing the temperature. Okay. So how did we do? We looked at the total HVAC, both electrical and both heat pump and strip heat energy, and we did a linear curve fit with indoor-outdoor temperature difference, and having some uncertainty in terms of the slopes of these two models, we can do a Monte Carlo simulation of the relative savings between the two cases. And this is what this resulted. Effectively, we had some expected savings of 19%. And then there's a distribution, and this is largely driven by day-specific dynamics, right? So the controller doesn't save as much energy on, for example, very cold days because you don't have a lot of shifting potential versus milder days, right? So that's why the savings are there. And in terms of the electrical power, this is the profile before the MPC and after MPC, and we can largely see that without MPC, we did use a lot of stage 3 electrical energy, whereas with MPC, it's primarily stage 1 and stage 2. Now, going into the summary slides and closing up the presentation, apologies if I'm going fast. So in terms of the development effort, the total project development time was 190 days. This is from the time that I started on this project until the controller was up and running. I should mention these were student days, so having courses and other things doesn't necessarily mean that all of these days were 100% effort on this, but just to give the rough schedule, I would say that the non-repeatable tasks dominated, and those were the sensor procurement, server setup and sensor communication, and API related issues. We did find that the manufacturer's thermostat was difficult to work with at times, and that is largely solved with open source. There are some open source thermostats with available APIs, as well as the smart thermostats that allow this kind of features. Repeatable tasks, I would say these were related to fitting specifically the RC model for this house, and those I would say are between 4 to 5 days. In the non-repeatable tasks, I should also mention the controller development and the model fitting development, but those you would have to do it only for one house and they would scale. So, the repeatable tasks are the much smaller portion, and they could even further be reduced. As mentioned, the caveat, this is the first deployment, and there was some learning curve, which should be reduced in future iterations as it was. In other deployments, we did. We had limited RC generation automation, which means that there was some human in the loop, which can be fixed with either having a high fidelity emulator, which we didn't have. Now, some limitations for the study, which were very interesting. So the controller seems to have converged two saving mechanisms. I would say the first is increasing the temperature at high COP periods. This is generally in the afternoon, where we will do some preheating or even surpass the indoor homeowner preference. And the second part would be the slow recovery from setbacks. And this is very important because maybe there is a heuristic there, either on the smart setback side or the temperature, which we could have tested and done comparably, but we didn't find something readily available, and it is something to consider in the future. Some heuristic controller in terms of some simple rule sets, how would it perform with respect to the baseline? Unexplored effects, we found some significant reduction in the number of defrost cycles. These were demand-based defrost cycles, so the manufacturer is monitoring the coil temperature before triggering a defrost cycle. And that was actually one of the main reasons we reduced electrical consumption, especially for the high stage strip heat. and we really couldn't understand when the experiment was concluded. We do have a physical explanation right now. Generally, reducing load results in reducing the building load results in increased evaporator temperature, which in turn means that we spend less time below the dew point, and we don't transfer a lot of frost, especially at high humidity conditions, namely overnight, right? So when we do the setback, that does help significantly in reducing the number of defrost cycles and frost growth in the unit. So that was something that we found surprising and worth exploring further. Okay, so that's the end of my presentation. Apologies for going a little bit fast. I would like to thank Center for High Performance Buildings, Purdue, ASHRAE, and NAS Foundation for supporting me during this work, as well as Trane Technologies with data for the unit and helping us with the thermostat. All right, this is the end of my presentation. Thank you for listening.
Okay, thanks so much, Elias. Let's do maybe like 1 or 2 minutes of questions for Elias, and then we will transition into Ozan's presentation. Ozan will talk about a reinforcement learning deployment in the same test house, and we'll kind of get to do a little compare and contrast. So, go ahead.
I have one question. Can you go back to slide 10? I saw you show some time series comparison between the baseline and MPC. So I'm curious about what period did you choose to compare these two? Because if you wanted to make a fair comparison, the baseline and MPC should have some similar or same weather conditions.
Elias, did you hear that question?
So the question was, how do we normalize and compare the controllers across different weather conditions?
Yeah.
Yeah, so the way we do this is we look at the daily average indoor-outdoor temperature difference, as shown in this slide. So that is a good metric to understand, because heat is driven through conduction between the indoor and outdoor environment. So the delta T is a good measure for normalizing for the both the reduced demand by having the temperature a little bit milder, as well as the difference in the weather. We could have also just normalized by the outdoor condition, but the savings of the controller would be a little bit further exaggerated, right? Because it wouldn't account that by the fact that the temperature was a little bit milder during the time of testing than with the historical data.
Okay, so let's just do one more question for Elias, and Nam Nguyen has raised their hand online. So Nam, why don't you go ahead?
Thank you. Thank you for your presentation. It's very good for me. My name is Nam. I am a PhD student from University of Central Florida. And I have a question about the modeling part that here you are using a almost linear gray box modeling, right? I have a question because I have been working on physics-informed machine learning and also some neural networks. So have you tried this model in the real-world systems, and how do you see about the information, kind of the performance of them? Because I did a comparison paper compare between physics-informed machine learning and gray box modeling, and I saw that for physics-informed machine learning, it has more accuracy model. We have more accurate, but I haven't tried it in control, especially for MPC, and haven't tried it for real world deployment. So have you tried before?
Yeah, I guess that's a little bit of a loaded question. So I will break it apart in terms of my perspective on this. And actually, I think it really well ties into the workshop and what Ozan will also talk about. But one of the challenges that of having a full black box approach, even a physics inspired machine learning, is the data need, right?
Yeah.
We were able to train the core RC counterpart with 4 or 5 days of data. And that's very important because this is, if this is a new home or a new development, you wouldn't want to wait a year until you're able to deploy the controller. So when you don't have data, and in reality, data noise and other factors do make the training harder. In real homes, especially when you look at 100 or 1,000 or 1,000,000 homes, it does become important to embed as many physical priors to your training process. So that was one of the reasons we used this approach, and that's just generally been my findings from the literature and from my own research, that we're not quite there, but I could be wrong. And there are some new methods in terms of transfer learning, as well as having some very widely trained models and then applying them to specific models that do seem to have promising results. I'm not a specialist, but I would probably say Greybox is reliable, and it is one of the reasons that when we looked at the wealth of the literature on this topic, maybe 90% were Greybox MPC studies of the field deployments, and only a small subset were with black box approaches or with reinforcement learning, right? So that's maybe 80%, but especially if we include both simulations and real experiments. But yeah, I would say that summarizes my thoughts. Does that help cover your question?
It helped me because I'm just working on academia and just simulation based. But I think Greybox is very suitable for real world system, as you mentioned. Thank you so much.
Thank you.
That's a great question. Thank you, Nam. And Elias, thanks so much for the presentation. Ozan, why don't we transition to you? And we have a half-hour coffee break after this, so if you go over a little bit, that's perfectly fine. And ideally, after your presentation, maybe we can do a little compare and contrast sort of discussion about the two approaches.
Yeah, I mean, hopefully I will be able to wrap this up earlier. Can you see my screen?
Yes.
Okay. Yeah, I kind of like repurposed some slides I had for another presentation. This could have been nicer, but I didn't have a lot of time for it, and I blamed the 2 World Cup games yesterday, which went overtime for it. So let me start. Some parts I may just skip through. But basically the motivation is like the same idea. Arash did like an amazing review of showing us that we have seen many simulation and some real world experiments on these like proactive controllers that do a great job. Many promises have been shown. You name the number, we can probably find it in there. Yet, most of the controllers we see in our houses are still quite simplistic, right? It's like PID, rule-based, or you are not even allowed to touch it. So we need more scalable controllers. I think that's where we were headed. And 2 main paradigms here have been like model predictive control and more lately reinforcement learning. And between these 2 paradigms, there are works that lay in this gradient. Some of them are black box MPC variants, right? Or some of them are model-free RL, which on the right-hand side of the spectrum, but that mostly requires a simulator to train. We started with differentiable MPC, which, unlike these methods, it enables end-to-end learning of dynamics and a control policy. And again, this is more of like a hybrid method between the 2. NuRL, which was a work in my lab that was done before I was there, advanced this by like implementing online learning on top of the imitation learning differentiable MPC has. So actually this whole thing started by like me thinking, can I just take NuRL and put it in this house? Well, there were some problems. Its model was linear with like no RC parameters you can infer from. And it had to work with a quadratic cost function that you had to manually tune. So because of these limitations, we ended up building IBEX RL, which is the RL implementation we ended up doing in this house. So let me just try to summarize IBEX RL in one boring sentence. So it learns a physics-informed dynamic model, which is the same RC, almost same RC network as the Elias presented. But it also learns a cost function. And this is unintuitive to some of you all, because right in MPC, usually you tune the cost. This is mainly because what we are doing is inherently a decision-focused learning approach where we learn a system dynamics model with an inherent cost function so that it has better controller performance rather than minimal state prediction error. We will talk about that more. And then we implemented an online learning loop. This is kind of where the RL piece comes in, where during online learning, we refine these parameters. And lastly, this approach is still able to support constraints. And again, we validated this in simulation and a month-long real-world deployment. So yeah, this is IBEX RL. This is kind of like how pieces come into place. We have constraints, we have quadratic cost parameters, and we have a system dynamics model that goes into the differentiable MPC policy. So IBEX RL, to get this agent working in the middle, you first do an imitation learning stage, then you do an online learning stage. And in online learning, you have two different gradient loops, one for the state parameters, one for the cost parameters. Let's look a little bit more into this. For system dynamics, in the imitation learning stage, again, we have an imitation loss. So that includes the export actions coming from the existing controller and export state coming from the existing controller versus the ones that you are predicting. You are using that to come up with the initial RC network parameters. In online learning, there's not really an export action anymore, so you actually start using only the state gradient to update this model. And then what we call state parameters, again, are the parameters of the RC network. I think I already mentioned this. In the imitation learning, we minimize state and action loss. In online learning, we minimize the state loss. The cost approximation we does, again, in the first stage, you fit the quadratic cost parameters of the internal solver using an action loss. But again, this limits us to this gives us a suboptimal yet somewhat safe starting point. But the objective function MPC had was not quadratic. So we had to come up with a way to make this internal quadratic solver work with a non-quadratic reward function. So what we end up doing is we were using the gradient of the cost function the MPC had, just the negative of it, to make it a reward. And using that gradient, we kept updating the quadratic cost parameters to basically just come up with an approximation of the quadratic cost parameters that will maximize the reward, which is again the negative of the objectives function of MPC. Elias already talked about these parameters, so I'm not going to go over the objective function again. Again, it's almost identical. The first experiment we did was simulation, but I'm assuming we are more interested in the real world, so I'm not going to talk too much about that. But we used Bob test, and it seems like Ettore is going to be talking about Bob test after this one. So pay attention. Bob test is really good, very useful. What we see in simulation was that from day one, like this is the day that it started to be deployed, we see some proactive behavior. Not surprising, because after all, this is a model-based reinforcement learning algorithm. And then we see that it does a better job making use of the heat during the midday period as well. So overall, compared to the new RL we built this on top of, IBEX RL does better. And then we compare it to some other methods such as Clue and some rule-based controller, taller bars, different comfort levels. Overall, what we see is that IBEX RL achieves most savings while still keeping people comfortable, which is what the color coding here shows. But savings could be larger. We did do an ablation study, and we saw that without exploration, you get up to 25%, right? The motivation for exploration, though, is that it makes your state loss go lower over time. Like in the beginning, exploration harms you, but then it provides you with more savings down the line. Is that really the case, though? We actually did do an analysis on that, and we saw that that's not necessarily the case. Like exploring more did not really provide any benefits to the RMSE we see for the system dynamics model. So there's more research to be done here, is what I'm saying. So now let's talk about the real world experiment. Again, it's the same house. The state disturbances are all the same. As the control input, we use power like MPC, but we translate that to a set point by using the next state temperature prediction because we cannot control the power. Yeah, everything else is same. But before going forward, I think at some point some of you may think why we are not using soft actor critic, why we are not using DDPG. Like there are other residential RL deployments out there, right? But besides the first one, which did not train anything, and it was like a more simpler environment, the other three require the simulator to train. So what they ended up doing is they either fit a model or an RNN, and then they train this RL algorithm, which is shown on this part, using that simulator. But we didn't want to do that because I think for RL to be somewhat scalable, we should be able to start without having any simulator to begin with. So that's why we basically went ahead with this approach, and this is again one of the longest residential RL deployments out there as well. So again, the benefit, the savings for IBEX RL is also coming from a similar point of view as MPC, where most of the benefit comes from either doing stepped increases when the user-defined set point changes, or gradually reducing set point before we went into the nighttime setback. And as you can see, by doing so, it's actually able to cap the power consumption at heat pump power limit and not turn on the backup heat, which again was the main source of savings. So overall, when we look at the savings between these three algorithms by doing linear fits, we see that IBEX RL and MPC achieved almost the same number. 21, 18, it's all within confidence interval. So we shouldn't say one is better than another here. Yet, it is clearly better for MPC in means of comfort. MPC had better PPD values, around 9.9%, while RL had 13.5%. Part of this was because of the initial adaptation period where RL was still learning the cost parameters, and especially during those few days, it assigned colder set points. And lastly, we make some like vaguely educated guesses on how much would it take to deploy these algorithms in new houses. If they don't have this IoT setup Elias was talking about, we are assuming that would take around 4 days or so for both algorithms. And after that, we are estimating 2 days of configuration work for RL, while 5 days of configuration work for MPC. But again, ideally, all of these numbers should be zero, because if an HVAC company were to do this, they couldn't afford an engineer. Like people couldn't afford an engineer from an HVAC company coming here and spending 2 or 5 days of their work into this model calibration period. Overall, we saw that IBEX RL had, up to 25% savings in simulation. Real-world experiments show comparable savings, but MPC had better comfort. We are estimating IBEX RL to require a little bit of less engineering effort by automating some of these model fitting and using operational data for imitation learning. But we still see that the initial adaptation of IBEX RL caused some discomfort, which future work should try to address. Yeah, overall, we work towards achieving interpretable and efficient building controls, and yeah, that's about it. Happy to answer any questions you may have.
All right, thanks so much, Ozan. Maybe we can start with any questions from the room.
Hey, Zach, very nice presentation. I have two questions for you. The first one is, so you said that you didn't use the simulation to train the RL first, but you initialize the meta parameters based on the study of the simulation. And the second question is, since in that initialization phase you could have discomfort issues, do you think it would be possible to deploy the RL in like a shadow mode where it could try to control the system but actually not controlling it and still try to learn the behavior of the build?
I heard the second question. Can someone rephrase the first question?
I can come both. The first question is just, you said that you didn't use the simulation to pre-train the RL, but
Yeah.
did you use it to inform the meta parameters then for the deployment in the building, or did you have to tweak them?
Which parameters you said? RC parameters or the
Like the hyperparameters?
Yeah, the hyperparameters of the RL.
So like the learning
Okay.
rate, for example.
Oh,
Yeah.
I see. Hyperparameters. Okay, sorry, I couldn't hear much. I should really buy new AirPods, but basically, no simulation was used for informing RL training, but hyperparameter tuning for RL was done. But it was done using, like, restarting the whole training, basically. We tried different learning rates, we tried different lambda values, and that was just a sweep of some pre-selected values, and then at the end of it, you take the one that returns the minimum imitation loss, which is what we did. So does that answer your first question?
Yes.
Okay. Yeah. And for the second one, doing a shadow mode is definitely possible, but the problem is in the shadow mode, you really still cannot use the online learning data you get out of it, because although it's shadowing an action, you are not really implementing it. So the next state is not based on that action, so it's not really becoming some useful data for online learning. What could be useful is if we were to use like some excitations in the training data for RL. We didn't. Maybe that could have helped. Or just going with the quadratic cost function could make this easier as well.
So to wrap up here, as we're getting into the coffee break, let me just ask, I guess, to both of you guys, speculate a little bit. If you were going to implement something, maybe an MPC, maybe an RL, maybe something else, right? But either you were going to start a company and do this in 1,000 homes, or maybe just you're going to do it in your own residence, right? What would you do differently from what you did in these field demonstrations? So I guess what lessons have you learned, and what directions do you think you pursue in the future?
Do you want to go first, Elias, or should I go first?
I don't really mind. I could go first.
Sure, go ahead. Yeah.
So I think it's a loaded question because it really depends on what your end product is, right? Are you looking to provide some grid services? Are you more homeowner facing, where comfort and their preferences are the most important thing, right? So it's a really open-ended question, but let's imagine that I put on the hat of let's say Google, right? I think what we've generally found, and also from Trane side, but also from what my experience was at Purdue, is data is scarce and generally quite noisy. So I think it goes back to the previous question we had before Ozan's talk. I think embedding physical priors to the models is important. Even if you have a model-free approach that does achieve the performance that you want, right? I think a part of the measurement and verification part does require you to be able to monitor what the space is achieving and how well are we doing. So I think having a model is important. So that's my general 2 cents. If, let's say, I'm a homeowner, I know intuitively that a setback is saving me energy, but then how much energy is it saving me? And what if it's a system, let's say it's heat pump with strip heat, and actually I'm using a lot of energy in the recovery period, that I see that on my bill, that my strip heat consumption goes up. So I think having models and being able to have some metrics that are homeowner facing is really important. And that would really be the biggest barrier to this technology on the residential side, right? On the commercial side, I think it's a very different question, different stakeholders, different orders of magnitude, but always comfort is a priority in a home, and engaging the homeowner should be the way to do it. I know you could just take over the system and start adapting the set points and tell them they are comfortable, but at the end, if they don't like it, they'll just go into auto or just keep the temperature constant. So I think homeowner engagement is crucial.
Thank you. Ozan, any closing thoughts?
Yeah, I think it's heavily dependent on what kind of an algorithm. Let's say I want to implement in my house. If I were to do this thing again, right? Due to personal biases, let's assume I'm going with like IBEX RL or a version of model-based RL. I think I would. This is something I learned in workforce now. Apparently, there's something called KISS method, which is keep it simple, stupid. So I think I will try to keep it simpler and stupider, which makes it easier to debug. And initial deployment phase, I would try to make that overlap with a warmer day when I'm not home as much as well. So I think, those kinds of like personal priors that are coming from, again, super biased opinions coming from specifically this implementation. But overall, if I want to make like general comments, I think we may need to let them know that there will be some discomfort either pre-engineering before the algorithm deployment by like setbacks or excitations, or during the initial phase during algorithm to like adapt a little bit. And I think if we communicate this with the homeowner, maybe that could make our job a little bit easier as well.
Great. Well, thank you both. I think we'll wrap up there and go into our coffee break. And when we come back, Ettore will present a little bit on BOP test and some of its applications, I think both for research and potentially for education.